thank you to everybody who's joining today for this extended introduction to our security specifications. I'd also like to just start out very briefly and then hand it over to Rick Wheatfield to start the content of the webinar. Just give a little bit of an introduction to Mipi Alliance. I'm sure many of you are familiar with it, but we want to give a little perspective on Mipi, and then we'll head into the content of the presentation. So Mipi, we're actually celebrating our 20-year anniversary this year. Surprisingly, it started in 2003 when first camera phones were on the market, and were really formed. The initial mission of the Alliance was to standardize camera and display interfaces. And obviously Mipi has evolved since then. The ecosystem really in response to the mobile ecosystem evolving in ways that we could have never predicted. And today, we see at least one Mipi specification in every smartphone on the market today. Developed more than 50 specifications covering a wide range of interface specifications for mobile. And obviously as mobile has impacted its ecosystem as well as impacted and influenced other ecosystems, we're seeing our specifications widely adopted in other areas as well. As the implementation has evolved, so too has the member ecosystem, from the original kind of founders of Mipi being the device OEMs, the application processor developers, the semiconductor companies, then evolving as Mipi specs were implemented in product, to test equipment, test labs, IP and VIP providers. We see automotive OEMs and tier ones joining Mipi, as well as a wide range of software and consumer electronics companies. So, in every given month, I'm surprised by the breadth of companies who are looking at Mipi Alliance and joining the Alliance, and more importantly, implementing the specifications. The left, or at least my left, shows the mobile system diagram, which is really the, mobile is the focus for Mipi, and we leverage member investments in other areas and evolve our specs to meet those needs as well. Beyond mobile applications such as automotive, industrial, consumer electronics, and heads-up displays, we see aviation companies joining medical, IoT as well. And our specs are royalty-free for implementation in Mipi member products. As I mentioned, Mipi, one of the beyond mobile application areas is automotive, and you'll see that, automotive really for the security specifications was the first driver. And we've since recognized that whether it's automotive or IoT or specific, camera applications, the security is important across the board. So we've kind of generalized it to support just security in general for a wide range of applications, but automotive was really an initial driver for us getting involved in security. I won't reference all those names, but you can see the wide breadth of Mipi members who are in automotive today. In addition to automotive, we've evolved through all of the various Gs. I hear people talking even beyond 6G and 7G. But 5G is really in its kind of in its infancy a bit. First forming shortly after the initial camera phones on the market, 2010, we started getting involved in CSI and DSI protocols evolving to meet the automotive requirements. Automotive working group started around 2018. And today we have a fairly large focus in automotive, to meet the needs of our members in the larger ecosystem. In terms of specifications in automotive, you see camera, CSI-2, display, our C5 and D5 physical SerDes. You see I3C, you see RFFE, Unipro and MFI in UFS, in JEDEC UFS, as well as AFI for longer reach SerDes. In terms of security initiatives, throughout the years, Mipi had discussed whether or not to develop or focus or concentrate on security. And it was always, especially in its early days, it was always seen as outside the scope of MIPI, or it was in the hands of the developers and resided at a layer above or below, MIPI specifications. But that really changed in 2019. Certainly, the need for security within automotive and being able to address and make sure that the camera feed or the camera frames that are being distributed around the car are secure. And so Rick and Phil will go into a lot more detail on that today. And so, security being added to strategic priorities, an investigation group being promoted to a security working group, looking at the security specification v1.0 SRP. And through that time, we've really evolved, even in that short period of time from 2001 till today, we've really evolved the approach and how the security specifications are coming forward. And I think, Rick and Phil will describe that to you in a lot more detail than I will here today. There's a lot of information on demand. You can go back and look, but our intent today is to really give a bit of a deeper dive on the security specifications and the framework, how we're approaching it, and to start to provide that to the ecosystem so that they can begin to evaluate their potential implementation. With that, today's speakers are Rick Wheatfield. I won't read his full bio. He's co-chair of the MIPI Security Working Group. He's also on the MIPI board as vice chair of the board. Philip Hawks is co-chair of the MIPI Security Working Group, and both from Qualcomm. Again, there's many ways to learn. You can join the security mailing list. This will be in the link is there, but it's also in the slides that will be distributed in conjunction with this webinar, joining the automotive email list. And so there's no shortage of information that we're putting out to the ecosystem. Obviously, to participate in the development of the security specifications, you need to be a contributor member. So if you have any questions about that, feel free to reach out to myself directly or contact admin@mipi.org. With that, I'd like to hand it over to Rick Wheatfield, who's the Security Working Group co-chair, and take you forward from here. Thanks, everybody.
Okay, let me find the cursor, the magic. So yeah, so my name is Rick Wheatfield. I am the co-chair of the Security Work Group. I wanted to just, before we start, just give a shout out to all the, the Security Work Group members. We've had a very busy, 2 or 3 years, and are, preparing to kind of finalize a series of 4 specifications this quarter. So in terms of the security introduction, one of the things that we want to do is highlight, essentially, why did MIPI do security? The short answer is, and Peter mentioned it, is really because of automotive. We don't need security in the smartphone, mainly because of the short distances and it's hard to get at. So really this was, fundamentally motivated by, by MIPI's entry into automotive. So MIPI is developing a framework for security. It will also include functional safety, but that's not really described in much detail today. And really the primary application is ADAS for automated driving. Essentially the scope of the security framework is CSI-2. And there's going to be a relatively in-depth review of what CSI-2 frames look like and how we're kind of partitioning the frame so that you could apply different security to different parts of the frame, which is a relatively new concept, within video security. So some of the key attributes, some of the buzzwords you'll hear are source selectivity. What we mean by that is that different parts of the frame can be protected differently. You'll hear application layer, which is you know, reminiscent or, you know, very similar to TLS. End-to-end coverage, by that we mean that the coverage, you know, begins from the sensor data and it goes all the way through a number of intermediate components like bridges and switches, things like that, all the way to the controller, the SoC. And then you'll hear for these four security vectors, the security protocol. We have two protocols we'll discuss, SEP and FSED. We have options for different types of cryptography, integrity tag modes, exactly how we form the integrity MAC, and different security protection levels, what we call security variants. So we'll go through these in bold. Here are just some of the buzzwords that you know, we'd like to try and focus on in the presentation. There are four specs in development. The MIPI security is a baseline spec. The security profiles are a mechanism to provide a set of very specific carve-outs or portions of security that that would help interoperate. CSE, the camera service extensions, that's really the application of security to CSI-2. There are others in development, including DSE for display. That's a different topic. And then there's an I2C-based security extension known as MIPI Command and Control Interface. It's built upon the existing CCI interface defined in MIPI Camera. So that's essentially the kind of the overview, and let's dive in. In terms of the agenda, we'll go through the security introduction. Essentially, what are some of the security you know, use cases. We'll go through the security extent. By extent, we mean two things. One is end-to-end application-based. We'll talk about that. Service layering. We want to. There's one short discussion on what we mean by the layering. How do you know if a security system is functionally safe and vice versa? Security flexibility. This relates to the you know, the level to which you can provide very granular security, you know, depending on the parts of the frame of primary interest and that sort of thing. And then Phil will go into some of the more details of the security framework itself. And then we'll, of course, have some time for questions. Okay, so part one, the CSI-2 security. So what are we trying to achieve? Essentially, this is, of course, a car. There are distances of 10 to 15 meters between a sensor and a controller. It's along the way, it will, you know, go across cables, connectors, bridges, switches, aggregators. And the idea is that we want to protect end to end from the source all the way to the destination. There are multiple sensors in a car. There may be, you know, we're planning anywhere up to, you know, 30 or so different CSI-2 based sensors. In addition, there may also be other sensors like radars and cameras. You know, any security person will recognize kind of the three tools in the toolbox. Authentication, which is, you know, fundamentally building trust between two components. Integrity, which verifies that the data is not modified in transit from the source to the sink. And then confidentiality, which is essentially hiding the data in order to provide a level of privacy. The threat that we're trying to accomplish by authentication is, of course, unauthorized components. Think of the printer cartridge example. You don't want a faulty cartridge. You don't want an unauthorized cartridge. You don't want an unauthorized sensor. By the same token, you don't want an unauthorized SoC. Of course, this is provided by authentication credentials. MIPI supports both certificates as well as pre-shared keys. In terms of integrity, essentially the primary objective is to ensure that the sensor ADAS data is not modified en route to the processor. And of course, that's nominally provided by the message authentication code. Confidentiality is through encryption. Use cases for confidentiality thus far in automotive seem kind of second order. The primary use case is authenticate the components and then provide integrity protection. This is a stack of the MIPI camera work group product. It starts from the camera command set up top and it ends in some type of physical layer. In mobile, it's C-PHY, D-PHY. Curiously enough, in many of the cases, MIPI C-PHY and D-PHY will also be there as kind of the first mile and last mile, or first foot and last foot, because there are bridges in the middle. We will go through some of the topologies in some slides later. Of course, MIPI A-PHY is the MIPI SerDes that's been in development for a number of years as well. MIPI Security lives near the top of the stack, nominally above the CSI-2, and we'll talk about some detail there in the upcoming slides. There are a set of 4 specifications, as we discussed earlier. So security extent, the security extent will cover topics like end-to-end and application-based, which I've introduced already. The reference topology. So when we got started, we were aware, of course, of the existing automotive architectures. There is typically, of course, bridges that provide long reach physical layers, or SerDes. And there, in some cases, there are these entities that can provide a multicast component. And of course, there's the controller and the sensors. So we put together this generic topology to try and capture the current, in-vehicle network. We gave them numbers. They're numbers 1 through 5. So whenever we talk about an end-to-end security, we typically mean or would reference 1 to 5. Shown on the bottom, though, there are different security extents that the MIPI framework allows. And in the first example, you can see that the SerDes are integrated into the controller and the target. The other examples show different security extents in which security is implemented, for example, only in the bridges 2 and 4. And then there's an extent of 1 to 4 and then 2 to 5. So the point of this is really to illustrate that the security framework allows the controller, the number 1 controller, to essentially establish security, between any of these endpoints, whether it's 1.5 or 2.4 or some of the other ones. Again, CSI-2 based security is typically implemented in the endpoints 1 and 5, but it can be done in 2 and 4. It cannot be done in number 3, which is a forwarding element, because the forwarding element would operate at the link layer of the SerDes PHY. So again, very flexible topology. There's a slightly different view that we sometimes illustrate, which is at the bottom, and that is that there's kind of a cloud representation for a SerDes network. And the basic principle there is that you can have any number of bridges or aggregators or other network components in that SerDes network cloud. Ultimately, the security is end-to-end from sensor to the controller. A couple of more complex topologies. Here we have 2 sensors, so 2 number 5s, and we have 2 controllers, 2 number 1s. Instead of 2 controllers, you could have essentially 1 controller with separate ports, so separate C-PHY, D-PHY interfaces. But for simplicity, we just decided to keep the 4 endpoints identified discretely. You can see in the middle, there's the cloud. In this particular example, the sensor 5A, its data stream is multicast to both controllers. The sensor 5B is unicast to 1 controller. Again, the idea is that sensor 5A, its security initiation is terminated in this particular case in both controllers. And sensor 5B, its MAC, if you like, is terminated in controller 1B. A different example of having an intermediate ISP is shown just for completeness. Again, the framework allows this type of establishment. You can have 1 sensor, number 5, whose CSI-2 virtual channels are multicast on the upper stream essentially the raw pixels from the sensor are terminated in the controller 1A, which verifies that MAC. The lower stream represents the ability, of course, to terminate the security in the ISP processor and then regenerate another integrity MAC for termination in the controller. So the objective of these slides is simply to illustrate that of these use cases is to illustrate that there are different topologies out there, and the framework allows for the establishment of security in all of these different topologies. What do we mean by end-to-end? Well, again, end-to-end, we refer to it as the data protection of the CSI-2 pixels from the original data source to the final data sink. In other words, it's independent from any of the intermediate entities 2, 3, 4. Or we can say that the extent is 1 to 5. By application-based, essentially it means that the data is protected from the original source at the highest layer. In other words, where the pixels are formed to where the pixels are sunk. A good analogy is this is TLS security. In the OSI stack, by application here, what we typically mean are the pixels. In some cases, we refer to them as pixel bytes. In other words, after the ADC conversion. So sometimes we use end-to-end and application-based, synonymously, but here we're just trying to be discrete in terms of how we define them. So another diagram on the layering on the left-hand side is really the mobile use case, where we have the applications at the top. We have CFI, DFI interface at the bottom. These are short reach, 10 centimeter, 15 centimeter-ish type of distance. And we have the CSI-2 protocol. On the right is an example using the MIPI A-PHY SerDes and the introduction of CSE, which is the camera service extension, above the CSI-2 layer. CSE, the services that are described are security and safety. And essentially the objective here is really just to illustrate the notion of application-based, which is the management, insertion, and reception of security at the highest layer. The other interesting comment is that sometimes we refer to this as application-aware security, so that you can apply different protections for different parts of the frame. Something we refer to as frame partition, and of course we'll talk about that in the next few slides. Before we do that, there's an issue of service layering, which is applied first, security or functional safety. This is a graphic to illustrate that, in fact, security is applied first in the transmitter. So what happens is this illustrates the source being protected or covered by a security MAC first, and then it is wrapped or subsequently covered by a functional safety CRC. And on the reverse side, the CRC is undone or verified first, and then the MAC. Certain failure indicators are then processed by a management policy that's out of scope of MIPI. Even though this is shown as a layered structure, and implementation can implement it in different ways. In one sense, it could implement them meaning the services, security and safety, completely independent of one another. But there's a lot of detail behind different options of processing in the receiver, and that will make an interesting app note at some point in time. Okay, so let's talk about the rest of my part. Will be focused on the flexible options that MIPI Security provides. First, we start with the anatomy of a CSI-2 frame. CSI-2 has evolved over the last 15, 18 years since it was originated for mobile. When we were thinking of adding security to it, the very first objective was really to start to define it in somewhat more tangible terms. We haven't modified the CSI-2 protocol, but what we've done is we've defined certain parts of it so that we could be more explicit. We have so we introduced frame partitions. We haven't introduced frame partitions, we've just given them names. So we have FP1, which is the frame start message, frame FP5 is frame end, and the middle ones, top block, middle block, bottom block, FP2, 3, 4. Those that are familiar with this would recognize the image data is always FP3, and then there's metadata before or after the image data. You know, the metadata could have GPS coordinates, could have sensor status, good pixel, bad pixel indicators, things of that nature. So we haven't touched the CSI-2 format, which has been, been used, for a number of years. So again, the very basic element of security is to define data plane protection and control plane protection. We've defined those separately. The speeds of the data plane, range from 1 to maybe 10 to 15 gigabits per second per sensor per camera. The speeds of the control plane are relatively low, essentially I2C based. At some point, they'll move to I3C. Typically, those are a few megabits per second. The two formats for the data plane protection are SEP, Service Extensions Packet, FSED, which is frame-based service extensions data. These are just names. And then CCI-SE is the I2C based. So these are what we refer to as data service protocols, DSP, or just protocols. We'll talk more about those in the next few slides. So this is a high-level comparison of the two protocols, SEP and FSED. The CSI-2 is shown on the top. It's just illustrating that there's a frame start packet, there's a frame end packet, and in the middle there are just CSI-2 packets. Essentially from left to right, you encounter the different frame partitions, FP1 through FP5, FSED, and then SEP. The easier one to maybe start with is SEP. We see these purple wrappers. Every CSI-2 packet is wrapped with a SEP header and footer, whereas FSED doesn't wrap or envelope any CSI-2 packets at all. In fact, it just introduces new CSI-2 packets. The reason for these two different implementations, one was that FSED was less granular. It only operated at the frame level, whereas SEP operated at the CSI-2 message layer or message quantum. If in fact you do need per message security, then SEP is your choice. If you only need frame-based security, then FSED is one choice. Later on, we decided that SEP also needed a frame-based mechanism as well, so that was added. A typical sensor, as we will discuss, will either implement SEP or FSED. The controller will very likely need to support both eventually, primarily because of the different cameras may independently support SEP or FSED. So flexible security, we've defined these four vectors or four key attributes of CSI-2 security. From going around the clock here, we have protocol, we have cipher suite, we have tag mode, and we have security variant. Protocol, we've introduced FSED, SEP, cipher suite. We've divided these up into a high grade and low grade or performance efficiency mode. Tag mode essentially defines how and how often you compute the MAC, and the security variant applies different security to different frame partitions. Most of these are flexible on a per frame basis. The protocol can be configured or is configurable on every sensor boot. Typically, a sensor would only support one or the other, but the framework allows the sensor to be boot up in one mode or the other, one protocol or the other. Cipher suite, we'll talk a little bit more about that, but we have essentially a CMAC and a GMAC, integrity selection. Tag mode, flexible per frame. Security variant is flexible even subframe. It's on per frame partition. So the flexibility is identified in the sensor. The SoC chooses from the options that are implemented by a given sensor. This is a different view of FSED and SEP. You can see that on the right-hand side, SEP essentially adds these purple headers and footers to every CSI-2 packet. On the left, you can see that FSED simply introduces 2 or 3 additional CSI-2 messages within the frame. So they're very different philosophy. Again, if you need a per message-based integrity protection, you use SEP. If you need a frame-based one, then you would nominally start with FSED. So the Cypher suite, just quickly, there are efficiency algorithms and there are performance algorithms, essentially driven by, in performance mode, you can apply AES counter mode encryption. You also would apply GMAC integrity, which scales. It allows hardware scaling, of course, to higher performance. And then in an efficiency mode, there is no encryption, and you can use CMAC integrity. Again, the SOC controls which Cypher suite is applied, both AES 128 and 256-bit keys are available. The third one is tag modes. So you can see here we have SEP tag modes and we have FSED tag modes. Again, the SEP applies a MAC, and it turns out a CRC on every single CSI2 message in tag mode 1A, and then moving left to right in mode 1C and D, there's a MAC only at very specific parts of the frame, and we refer to SEP tag mode 1C and 1D as per frame based. And then in the middle you have mode 1B, which identifies a MAC at every data type transition. FSED mode, again, a different perspective of how these 2 or 3 FSED messages, FSED CSI2 messages are interspersed throughout the frame. So again, tag mode is essentially one in which you define when and how frequently you're computing and transmitting a MAC. Finally, security variant is the fourth security vector, if you like. The interesting part of this is that MIPI is introducing something called partial integrity. Here, partial integrity is identified as security variant 3 and 4. On the two ends, we have security variant 1, which is essentially full integrity and encryption on. So it's the highest relative security level. Number 2, SV2, essentially turns encryption off, but it's essentially the same relative security level insofar as integrity is concerned. And on this, in SV5, there's no integrity, no encryption. And then the partial integrity options, essentially this applies the option, or this provides the option to only integrity protect some of the data, whether it's in horizontal lines or vertical stripes. There are a set of parameters that identify which of these SVs are applied to which frame partitions, and the setting of partial integrity is accomplished through parameters that we call stride pattern. So the stride is obviously this skipping of some of the portions of the frame. This is a more explicit example of how security variant can be applied differently to different parts of the frame. In some cases, we refer to this as source selective. In other words, you can apply security very specifically to different parts of the frame in different ways. So you can see here that the frame partitions are identified FP1 through 5, and we have these SV options, SV1 through SV5. So you can see that, for example, FP2, the top block, has 4 options for security variant, which is also true for FP4. Again, FP2 and 4 essentially contain metadata that describe the particular video frame. The middle block, FP3, is the image data, and it can support all 5 SV security variants, including the stride pattern that's defined in the partial integrity modes. Again, it's the SoC that controls these options um, for each video frame. How often can you change this particular setting? In principle, every frame, but in practice, it would be less frequent. Okay, this is almost my final slide. This is a security landscape. This is a essentially a one-pager for how MIPI CSI-2 security is identified. It has the 4 vectors that are pointed to in this table. You can see the protocol, SEP and FSED. You see the tag modes 1 and 2. You can see the cipher suites in the bottom that are a function of the different protocol modes, SEP and FSED. And of course, you have the security variant, the SVs that are mapped in certain ways to different of the frame partitions. This is the last slide. Essentially, it defines a really important, what we call an object, a programming model object. The security context, essentially, it identifies the complete security settings or context for a particular virtual channel. There's one security context per virtual channel. If you have multiple virtual channels in a system, you may have 10 or 20 virtual channels across 10 to 20 cameras. Then every virtual channel is uniquely defined by its security context. All of the framework vectors are captured here. The security context is established through 2 commands. One is sa-config, the other is control-config, and they define certain parts of the security context object. Phil will go into more detail as to how these parameters are, fit within the overall framework. And the objective, of course, in MIPI security is to have the SoC go through a very concrete, what we think is a well-specified set of steps from boot up all the way to setting up the security context for each of the virtual channels. So with that, I think what we'll do is hand over to Phil and have him walk through, some of the more detailed features of the security framework.
My name's Phil Hawkes. So Rick has gone through the description of how to secure CSI-2, and he's finished up with the concept of a security context, which is maintained at the sensor and the SoC, and the idea being that both endpoints will be doing the same thing. They're doing the correct thing when they're doing the security processing of the CSI-2 frames. And this security context is always controlled by the SoC. So my half of the presentation looks at the MIPI security framework, which covers how we do authentication between the sensor and the SoC, and how the SoC manages the secure context on a sensor. The security framework is intended to be used for managing the security context of any security protocol, which is used for protecting MIPI protocols. So this presentation focuses on SEP and FSED, which are used to protect CSI-2, but we can also use this framework for protecting the CSI-2 control channel, which is called CCI, which is transmitted over I2C, for example, or for protecting DSI-2. I'll spend the most time on the framework introduction, which explains how these different bits and pieces fit together, and then I'll give a brief overview of the security protocol and data model, SPDM, which is specified by DMTF, and is what we use for authentication and setting up secure connections. for managing the security context. And finally, I'll discuss the security profiles for SPDM, which specify all the a set of options for SPDM to aid interoperability. So the let's go to the framework introduction. MIPI splits the security framework into 3 levels, and they have separate security objectives. So these aren't protocol layers, these are 3 different sets of functions or objectives. The description assumes, and so what's shown here assumes a simple scenario where the sensor, or the sensor over here, applies the SEP or FZ, and then transmits that back to the controller, to the SoC, and the SoC here has 2 functions. First, it's controlling what the SEP or FZ processing is that's being applied at the sensor using this let me get my pointer. So that we have, we have the control channel going through across the top here, the security control channel from the SoC to the sensor. And then secondly, after the sensor has transmitted the data back to the controller, we have the controller SEP or FZ agent is processing that FZ and SEP to verify the data and optionally decrypt that data. We're going to start our description down here at the bottom level. So the goal of the security framework is to enable security protecting the MIPI data using a data service protocols. So this, you can see data service protocols, or DSP, here in this bottom pink level A. The data service protocols protecting CSI-2, SEP, and FZ, shown here. That's what is described by Rick in the first half of this presentation. So really, we don't need to go into too much detail into what's happening in the data service protocol here. And the data service protocol is controlled by configurable security context parameters. And really, the rest of the security framework is describing how the SoC manages the security context over here in the target. The protocols involved in managing the security contexts, or at least securely making sure they're secure, are in this middle lavender level B here, the System Security Management, or SSM suite. The SoC and the sensor both include logical entities here that we call the SSM controller and the SSM target, respectively, and they're what does the SSM processing. The processing is common to all pink data service protocols. So whether you're protecting CSI-2, whether you're protecting CCI, so the control channel, or whether we end up whatever other security protocols we define, the idea is that this pink level, lavender level here, level B, can manage any of those. Each DSP, though, will have different logic used to make decisions about the security context, because they all work in different ways. So we have a DSP-specific security context logic management function here. So this yellow box here is proprietary. So the decisions about security context, MIPI doesn't tell you what decisions need to be made and conditions and all that sort of thing. That's outside the scope of MIPI. There's another thing that, so in addition to making decisions, we also have different sets of parameters that need reading and writing to the sensor. So if we go back a few slides to slide 38, we see we have these SA config parameters in this column here, and we have some control config parameters here. Now, all of these can be controlled by the SOC. So that these serve different functions. I won't go back into those. The thing is that we need to update. So all the SA config parameters, the traffic keys and the cipher suite, all these sort of things, they all need to be updated or configured together in a single operation. We don't want to update one parameter at a time because that can cause problems. Same thing for the control config parameters. We update everything together. So we need to define data objects which contain all these different parameters so that we can format them and send them across from the SOC to the target. So that's these blue SSM objects. That's the term that we use for them there. So for each protocol, we define SSM objects. So for SEP and FZ, we need to define them for SA config and for control config. For other protocols, you might not need two separate configurable. You might configure everything at once. So that's what these blue is representing, is these formatting parameters into data objects so that they can be pushed across and applied in a single operation. And yeah, each of these objects, because there's different parameters for each protocol, each of these are defined for each protocol. So there's SEP, FZ, SSM objects. So that they actually use the SSM objects are the same for SEP and FZ because they have the same set of options. So in order to secure transporting these objects from one side to the other, we need to establish security, and so we need authentication credentials to establish this secure connection between the SSMC and the SSMT, and that's what this top green level C, the system security provisioning, does. That's the mechanisms by which you provision these authentication credentials, which could be certificates or could be pre-shared keys. Now, MIPI doesn't define the mechanisms that are used here. So this green level C is out of scope. It's up to an OEM, it's up to its vendors to work out those details. MIPI only describes what authentication credentials need to be provisioned, and we'll discuss that in a couple of slides. So in summary, the focus of the security framework is this system security management, the Lavender System Security Management Suite, and its function can be summarized as securely reading and writing these blue SSM objects on the sensor. And the security here that's established for level B uses the authentication credentials, which are provisioned by the green system security provisioning. So that's how all these bits and pieces at the highest level fit together. So now we're going to drill into pardon me. Now we're going to drill into the security framework. Into this level B, because it is not just one thing. It's actually got more functions in it. We've split it up into 3 different functions here. On the right-hand side, we've noted what the protocols are that we've specified for each of the functions shown here. Some of them are proprietary, for example, the SSM management logic and the level A. Oh, this is all mixed up. It's supposed to be level C up there and level A down there, so I apologize. The system security provisioning, that's implementation dependent as well. So within the SSM suite, the first function that we have is authentication. And this is where the SOC verifies that the sensor is OEM authorized, which is one-way authentication. The other option is that both the SOC and sensor verify that each other are OEM authorized, and that's mutual authentication. And this uses DMTF's security protocol and data model specification that provides the authentication and also establishes session keys. So when the authentication is successful, the SPDM outputs the session keys. These are used in the second function, which is the secure transport between the SOC and the sensor. And DMTF has also specified another protocol called DMTF secured messages, and this provides the secure transport function. And the secure transport, what is it transporting? It's transporting messages for the third function. This third function is reading and writing these blue SSM objects defined for the DSP. And we've defined a protocol which we call the SSM object exchange, or SSMOE, for this function. It's a very simple protocol, so I won't go into further details. There are other functions which are defined in the SSM suite to facilitate using the I2C interface. These aren't relevant to the security. I mean, they're needed, but I've skipped these functions. These are the three main things to focus on. Okay, this is the pardon me. This is really this is the guts of my half of the presentation, showing how all the smaller pieces and bits and pieces that we have, how they all fit and interlock with each other to create a working system. So there's two grey boxes here. The number one controller SOC, and then there's the sensor over here on the right. And notice that except for this yellow security context management logic function, each function in the SOC otherwise has a corresponding function in the sensor. So there's, so let's start at the top. So this is the green level C, the system security provisioning. So this mechanism is proprietary, and either certificates or pre-shared keys can be used. When certificates are used, then we sort of use this first row. Then the sensor has a private key for generating signatures that will be used in generating signatures in the SPDM protocol. And there's a corresponding public verification key which can be used to verify those signatures. And so the SOC is going to need that public key, a trustworthy public key, which it knows has been issued to an OEM authorized sensor. So if the sensor is OEM authorized, then the sensor is going to be provided with a certificate, which we've called certificate T here, which contains the public verification key and chains, I won't go into too much of the detail, but chains to a root of trust, which is used to validate certificates which have been issued to an OEM authorized sensor. And that root of trust gets provision to all the SOCs. It may be a root of trust that's applicable for a particular OEM. It may be, it depends on the system. There's various ways you can do that, but let's the root of trust for all certificates then issued to sensors that are OEM authorized. During the SPDM handshake, I sort of kind of mixed, this description is going to be a bit of a mix between the purple DSP, SPDM description, the purple SPDM description, and the green. Excuse me, I've just had to turn off my video. I'm having bandwidth issues. So during the SPDM exchange, initially the SoC doesn't have the certificate sensor because each sensor has its own certificate. So when you install the sensor and when you switch the system on, the SoC is going to request the certificate of the sensor as part of the SPDM. The sensor will send that to the SoC, and the SoC can validate that against the root of trust that's it's been configured with. And that's how it verifies that the sensor, that the certificate was issued to a OEM authorized sensor, but then it additionally needs to get the sensor to sign the to generate another signature using the private key as part of the SPDM handshake, and send that signature to the controller. That's a signature generated in real time, and then the SoC will check that signature and verify then that the entity that's talking to knows the private key for the public key that was in the certificate. So that's how the SoC verifies that the target or the sensor is OEM authorized. Now, if the sensor does not need to verify in some cases, some OEMs might decide that it's enough for the SoC to verify that the sensor is OEM authorized, but the OEM might not care whether the sensor verifies that the SoC is OEM authorized. So in that case, you don't need any more certificates in the system. That what I've just described is enough, and this is one-way authentication. But if the sensor also needs to verify that the SoC is authorized, then pretty much you go and what I've just described, you just reverse the roles of the SoC and the sensor, and you end up the sensor is a root of trust for the certificate issued to the controller, and the controller is the one who gets issued a certificate and ends up signing something to verify who it is. I know that's a very brief overview of how the authentication works. So in that case, so every device is going to have a unique and secret private key, which is not known to any other device. So if authenticating the SoC, its private key is going to be separate, completely different from the private key that's issued to the sensor. So this is one way of authenticating. The other is to use pre-shared keys. If pre-shared key authentication is used by a sensor, then that sensor gets provisioned with a unique secret value called PSK, and in system that's you and the SoC eventually needs to get a copy of that pre-shared key. For each sensor that has a PSK, the SoC needs a copy of that sensor's PSK. So the SoC can end up with multiple PSKs. The shared in pre-shared key refers to the key in the sensor ending up being shared with the SoC. So this same PSK ends up in the SoC and the sensor, as opposed to certificates where private key here for the sensor is different from the private key of the SoC. So it doesn't imply that the key is shared among multiple sensors. Every sensor has to have its own pre-shared key. So MIPI only uses two-way mutual authentication with PSK. So once these two both have a PSK and the authentication is done, then they've mutually authenticated each other, whereas certificates allows one-way as well as two-way. Okay, so that describes level C and half of level B. So as we just said, these credentials end up provisioned by the green level C, are input to the SPDM protocol in the lavender level B. The SPDM handshake is then performed as the first. So this system security management, it is initiated every boot. So this is a one-off operation, level C. This might just happen when you install a sensor, or when you're manufacturing the car, or if you've got to repair it and replace it with a new sensor. This root of trust actually only needs to happen once. It doesn't need to happen every time you replace a sensor. The but this level B starts. Step 1 happens, you do the authentication using the SPDM protocol. That happens when you boot up, and that results in one-way or two-way authentication, and outputs session keys denoted by SK here and here. They're at both the SoC and the sensor. These session keys are then input to this step 2D, which I'll come to shortly, where the DMTF secured messages is used. And it's going to protect all the messages that come into this DMTF secured, go through the DMTF secured messages protocol. It doesn't protect all the messages between the SoC and sensor. The SK are only used to protect those messages used for system security management. So only these SSM OE messages. There are also additional SPDM messages that can get protected by the DMTF secured messages. All right, so after this SPDM handshake, then the logic, the security context management logic can start reading and writing security context parameters on the sensor at step 2A. That can read the security capability. So we haven't discussed all the different SSM objects that there are, but there's an SSM object that contains the security capabilities of the sensor for F7 and FZ, so those can be read. And once it knows the capabilities, then the management logic can start writing SSM objects containing the configurable security context parameters. That's the SA config and the control config SSM objects that we discussed a bit earlier, which will be used for providing TK to the sensor, and also any of those other security context parameters. Okay, then step 2B here takes a layer below the security context logic and inserts the set or said security context parameters that are going to be into SSM objects prior to sending them across to the SEP across to the SOC. So the security parameters, the context parameters become these SSM objects, and then they get sent across here, and at the corresponding function, these get back into SD parameters that can be used by the SEP and FZ agents. Step 2C, now it takes all these different read and write requests and package them into SSM object requests and responses. So rather than so you can send multiple messages, multiple objects simultaneously across to target. Don't need to go much more into that. Then those messages get passed into the DMTF messages that create pass them across into the kernel, which is so these are encrypted and the target. It verifies messages and decrypts them, gets the SSM OE messages, and then breaks up into the different SSM objects. And those SSM objects, then the SSM objects, the SC and this passing those security down to the FZ agents. Now, it takes a bit of time. It's very closely synchronized when these devices, when the SoC and sensor receive these messages with these SSM objects. And so before providing, before we start executing those security contexts, there's a synchronization which happens at the start of the next CSI CSI-2 frame. So after receiving these objects, SSM objects, at the start of the next frame, the target transmits information which tells the OC yes or no that needs to switch to the new set of the new security context. And then once they're synchronized, then the agent execute the security context to provide integrity and optional encryption. Okay. Pardon me. So we've gone through this figure. So that was a lot to go through. Now we'll start looking in more detail at the SPDM protocol, which we use in step 1A for authentication and establishing the session keys. And then we'll look at the security profile. So let's move on. So the SPDM was defined by DMTF. This is a public specification. You can Google DMTF specification, SPDM, sorry, or look for DSP 0274, and you can find the SPDM specification there. And the SPDM also is a set of DMTF standardized messages which are based on TLS. So it's handshake is very into the TLS 1.3 handshake, and it's used for establishing secure connections between components. It's designed for embedded systems. MIPI leverages these SPDM messages, so we just use what is specified, but we have profiled each message specifically for authentication that's used for CSI-2. So our profile spec will say exactly what needs to be in each message to make sure that it make interoperability as easy as possible. The call flow can be illustrated in graphic form. It's shown here. It's easier to follow in tables, but I will zoom in a bit to try, and I'm not sure how I can move around I'll just show here. Oh, that moved it. We have the certificate-based and PSK-based flows here. As you can see, the certificate-based flow is a lot longer than PSK-based flow. And the main reason for that is that there's a couple of these boxes here that are to do with exchanging with the SOC getting the certificate from the sensor, and we've got mutual authentication, the sensor retrieving the SOC certificates here. As you can see, these add quite a lot of message. Pardon me. Now, not all of these messages have to be transmitted every time. We allow transmitting, we allow, sorry, I just got lost there. Let's have a look at the next slide, which will explain in a bit more detail. Oops, I think that's the right. So this table shows the messages from the previous line, except we have requests and responses. So everything in SPDM has a request transmitted by the SOC with a corresponding response by the sensor. So for every version, you should get a version message back. And the last two columns here indicate whether or not that message, that request response pair is exchanged in the call flow or the PSK call flow. A Y indicates it's always transmitted. A Y star is means that it's SOC and SOC exchange. If they've already exchanged the information, then they don't need to repeat this step. Optional means it's an optional feature, and no means it's transmitted. We'll go through these phases here. There's break it up into 7 phases. The first one is one where the SE where you can check the version, which version of SPDM we're using, capabilities specific to SPDM. So, does it use certificates? Does it use PSK? Does it do mutual authentication? Does it support measurements and so forth? And we negotiate the cryptographic algorithms. So after this first step, the S know everything they need to know about what's going to happen. So after that, if the SOC needs to get the sensor certificates, then it exchanges this. I won't go into details here, but this obviously only applies to certificates. And then we have the first 2 exchanges in initial exchange, of handshake. So we handshake one for certificates, exchange one, and then one for PSK, which is the PSK exchange. PSK exchange request response. After those first 2 messages, if you're doing exchange and if you're doing mutual authentication, then the sensor might need to obtain the SOC certificates. So we get some more requests here. Again, you only need to do this if the sensor needs the certificates. If it's one-way authentication, you don't need to do this. Or alternatively, if the sensor has cached the certificates, or at least cached the key and as a trusted public key, you can skip these steps because you know that you know that will be okay. Know that you have enough information, and after that, then the final check is 2 more messages that get exchanged for the finish and finish response with certificates, or the PSK finish and PSK finish response PSK. After that, we start the DMTF. After this has finished, then you can generate the sessions and start the DMTF secured messages, and then you can start sending messages that are transmitted after are secured. So any get measurements or measurements can be exchanged, or pardon me. Also importantly for us, the SSMOE requests and that could be response can be exchanged. Just one final point when talking about SPDM, I mentioned measurements. So a measurement is a representation, this is defined in the SPDM spec, representation of where software or configured data on an endpoint. So this representation can be either raw data, the configuration data as if you want, or it could be a crypto hash of the data, for example, a hash of the firmware or software. The controller, the SOC, selects what data it wants to retrieve, how it wants to represent it. For example, does it want the raw data or a hash of the data? All this is specified in the SPDM spec. MIPI is not defining additional stuff on this, and we're supporting using it. So measurements can be, individual measurements can be retrieved after the SPDM handshake tech DMTF secure messages session, but there's also an option which I've got right here, and that is that a summary hash can also, a measurement summary hash can be after the SPDM handshake. Sorry, during the SPDM, as part of the effect, so you can verify the measurements while you're verifying the SPDM handshake. Okay, my audio is not very good at the moment. So at this point, Rick, are you okay to take over from me?
Yeah, sure. It looks like you've been fighting the bandwidth gods. Yeah, I can do it, and then we can.
Rick, can you hear me?
Yes, can you hear me? Hello, can you hear me? Testing.
Rick, we can hear you.
I
Thanks.
can hear you now.
Sounds good.
Okay, got it. Thanks. Yeah, so we're almost at the end. There's just a few more pages on profiles, and then we'll move into Q&A. So yeah, can we move to the next slide? Not sure if I have control or not.
You should have the.
Yeah.
Yeah, got it. Okay, right. So the concept of profiles is not new to a complex spec. MIPI has identified a set of profiles, a set of initial profiles for camera in the MIPI profile spec. Part of the motivation is that SPDM, the handshake, has many options, and the idea is that you know, we want to identify a particular subset. In fact, 4 different subsets depending on kind of high-level choices. Essentially, of course, each side of the SPDM handshake has to have the same set of parameters. They will simply use the same profile, and then the handshake will work. The basic idea is that once the handshake is initiated and is successful, then essentially the system is up and running. So the MIPI security profile spec is essentially defining. Right now, it's four profiles, and it's essentially the minimum set that the work group has identified. The idea is, though, that in the field, you know, new profiles, you know, can be added as they're needed. Some of the algorithms here are the key profile algorithms for 128-bit security. These are standard in the field. You know, MIPI is not inventing these. There would be, of course, a different set of algorithms for you know, for 256-bit security when that is needed. And again, you know, there were essentially a number of the main kind of characterization of the profiles is having to do with authentication. There are options for using certificates as opposed to PSK. There's also the difference, as Phil has described, between one-way versus two-way authentication. You know, some of the interesting questions that have come to us before this webinar is, you know, does MIPI support the right to repair? And essentially, you know, one of the answers is yes, with certificates, the right to repair, namely the ability to kind of replace a defective component with an authorized and trusted component, is certainly possible. It's more, you know, it's more straightforward to do that with certificates rather than, say, PSK, but it does come at a cost. Certificates are generally large, somewhat bulky, and it takes longer to process. And of course, this in some sense runs counter to having a very fast boot that automotive requires. The issue of one-way versus two-way authentication is also there. One-way authentication, and this is our you know, member input thus far, is that one-way authentication is sufficient if CSI-2 integrity is the only security objective. In other words, the SoC should only trust data from verified or trusted sensors. So that one way is sufficient if you're dealing with integrity only. Two-way authentication can be desirable for other objectives, but increases complexity. So for example, CSI-2 confidentiality may be needed if only authorized SoCs can view the sensor data. So in other words, if you do require that the SoC can use sensor data, then certain steps are required. Another example is preventing an unauthorized SoC from controlling the sensor. So there are different interpretations of when you would require or use one-way versus two-way authentication. MIPI provides the choice through these profiles. The initial security profiles, there are 4 of them. There's a certificate-based one-way authentication, a certificate-based two-way, a PSK with two-way, and then a particular method that uses pairing to essentially improve the boot time by having an infrequent certificate-based handshake followed by kind of in the field or real-time PSK handshake. So these are the profiles. There are 4 of them. They are in draft form in the MIPI security profile specification. So I think we're wrapping up near the end. Let me just close, and then Phil and I will take questions. So we're developing this framework. The idea is that it's a quite flexible framework. It has these attributes that we've gone over in some detail here. We will make the slides available after, so you can, we can take a look. The 4 specifications are due relatively soon, and a key point of this is that we actually spent some time determining what the right name for this is, or what the scope is. There was some thought that this particular first spec would be focused on camera, and that's essentially how it worked out. And that was what broke up the specifications into CSE, application specific for camera, versus DSE, which is another effort for security for DSI-2. But the base security specification, of course, is common. The key part is that this CSE specification for CSI-2 security can be used wherever CSI-2 goes. So it's not only restricted to automotive, it's not only restricted to, to any particular physical layer SerDes. Further information is available. With that, let me hand over, I think, to Ian to kind of guide us through any questions that may have come in. Oh, I see one question in the chat. One question. Since the strategy for supporting FUSEN security is TX security first and TX FUSA last, this means that the security components must be developed to the same ASIL level as the application. Why was this strategy chosen? So that's a fair question. Phil, you hear that question? You may want to chime in as well. I think the somewhat glib answer, or the kind of easy answer, is that we had to choose one. You have to do one and then do the other one. We also wanted to make sure that functional safety was viewed as kind of the overriding, the overriding principle was that you need to have functional safety first. That essentially meant that it was the outermost wrapper to the transmission as it leaves the sensor. So that was the primary mechanism. There are active discussions in the ecosystem about the use of function, or the implementation of functional safety and security, but that's the current strategy that MIPI applied. I don't know, Phil, if you have any other kind of comments on that.
So this is so I'm not a functional safety expert, and to interpret my answer as not being from an expert, but from my understanding of functional safety. So functional safety can be considered looking at environmental errors that get introduced by the environment. So whether that's bit errors, whether that's dropped messages, so that they seem to be the 2 initial key things that are applied to messages. Has a message been dropped, or has a message been has there been a bit error up to 3-bit errors in the transmission. So if you're looking at accidental errors, then it makes sense to look to apply that sort of metric to a message once it's already secured, because once a message is secured with a message authentication code, then the message authentication code will it will detect any number of errors. It will detect one bit. It'll detect, pretty much any number of errors, any number of malicious errors. So with a security functionality, we're looking at that protecting against malicious messages, malicious errors, and functional safety, looking at accidental errors. And so we see functional safety as sort of being the first thing that can detect those environmental errors and say, hey, there's been an environmental error, there's been a bit error here, or a drop message, and that can report that up. And simultaneously, we're also, and that we believe should be applied, we understand that should be applied to the messages, the encrypted messages that are being sent across a connection. So that means you've got to encrypt first, then apply the functional safety, the CRC, to be covering the message, whether it's encrypted, to the encrypted message as well as to the message authentication code, to see whether there's been any bits dropped, any bits changed there. So that's how we came to that decision. In terms of your comment about the ASIL, I don't know enough about ASIL to comment on that, but I will certainly go and have a look into your comment and to make sure I understand, so I can provide an answer in the future. Rick, back to you.
Hi guys, it's Ian here. Can you hear me now?
Yes, we can.
Yes, I think you couldn't earlier. So we've just had the one question submitted, which is the one you just answered. So I'd urge anyone still on the call, if they have a question, please submit it ASAP. Obviously, we have a couple of questions up our sleeves that we have just in case we to buy a bit of time for our audience to submit their own questions. So we can run through those if you wish, guys. I think the first question we have was around authentication credentials and whether credentials could be shared between system components. I think you touched on this during your presentation, but perhaps we could touch on that point again. Phil, Rick, which of you would like to take that one?
Given my audio issues, I think it's probably best for Rick to answer.
Yeah,
Sorry, Rick.
Can. Yeah, so can authentication credential be shared among different system components? The basic answer is no. Essentially, again, there's two choices for authentication credentials. There's a certificate or there's the PSK, the pre-shared key. Essentially, the norm is that individual system components, whether it's a controller, sensor, or bridge, essentially they're provisioned with their own credential. So yeah, the work group had been asked to clarify that along the way. So essentially the answer is each component has its own credential.
Perhaps we could just sort of drill into that one. Obviously, you could have a component, a sensor. It has a data stream for the image data, but also perhaps has a command and control channel, a side channel. Could they potentially share the same credentials, or again, would they have separate credentials for the data stream and the command and control channel?
Right. I mean, our baseline that will largely be implementation dependent. Typically, though, we would recommend that the data channel and the control channel be secured separately. Now, that does not necessarily mean that they would have the. If Phil can chime in as well, they may actually you know, the module, the sensor module itself would be would certainly have its own credential, and then it would derive separate keys for data versus control plane. But again, kind of the one credential per component is generally the rule.
Okay.
So if
Sorry, Phil,
we
yes,
have a
please chip
quick
in, yeah.
Sure. If we have a quick look at this slide, so the authentication credentials are these green things that we're talking about up the top here, the certificates or pre-shared keys up the top here, and they're used to establish this secure DMTF secured messages via SPDM. Once you've got this secure channel, then you can. Oh, okay. Sorry, I wasn't the presenter. Am I showing slide 44?
You are now, yeah, absolutely. I was just about to interrupt you, Phil, but it's been corrected, so yeah, we can see.
Okay, cool. So yes, the authentication credentials are in green, up the top, and that's used to establish a secure connection that between the two 2Ds here. Now, once you have that connection, for each data service protocol that you have here, so we've got SEP or FZ for the data channel, and then we'd have something else we call CCISE for the control channel. For each of those, you would provision separate traffic keys. So you'd have your SEP or FZ traffic keys that you'd provision, and all the other configuration that you'd provision for SEP or FZ. And then just imagine there's a CCISE agent below these, which are being used for protecting CCI, the camera control, the command and control interface. Then those would be provisioned a separate traffic key, and also have other configuration parameters that would be configured for those. So they're both the security. So at this level down here, we've got separate credentials which are being used, separate traffic keys which are being used for SEP and FZ compared to CCISE, but the securing that channel, they both rely on a single credential up here, which is used to establish the secure channel.
Okay, Phil, that's good answer, I think. We've had another question actually come in, so let's switch to that. The question is, why so many parameters and modes? If implementing an SoC that wants to support multiple sensors with different parameters and modes, there is now a large verification space. So I guess it's alluding to the issues around interoperability and test and verification.
Right. Well, I think there's a short answer and a long answer. You know, the short answer is that there were, you know, every particular feature was requested by a workgroup member company. So, and of course, we tried to narrow this down. Profiles will help. Profiles, though, typically are associated with the SPDM handshake, you know, to set up the basic secure connections. But yes, there are lots of modes. It's very likely that very quickly, you know, a small number of these will become dominant. It does appear, though, that the SoC will need to take most of the burden in supporting, you know, many, if not all of these modes. So I don't think there's a clean answer other than it's what the members requested.
I'm guessing that perhaps what a lead-on question there is regarding things like obviously you have the profile specification coming, but we also have, MIPI does tend to release app notes, which perhaps offer some clarification in terms of to help implementers. Can you talk to what potential app notes might be coming, Phil, Rick?
Well, yeah, I mean, I can certainly start. I mean, one app note that might end up, you know, being in an annex of one of the specifications is essentially something that defines in a standard way the capabilities of a sensor. So a sensor would advertise its capabilities. I only support mode 2A, and I only support mode 1C tag modes. In that case, you know, the SoC would be able to quickly understand, the capabilities of that sensor. So at the very minimum, that would be one of the first examples of either a app note or a annex to one of the specifications. Another app note might be, under what conditions would you recommend, or what are the pros and cons of one-way versus two-way authentication? There are a number of such topics that the work group has identified, that would, help kind of, form an implementer's decision.
Okay. Okay, thank you, Rick. Just one eye on the time. Obviously, we're slightly overrunning here, but I think we should cover at least one more question. And that's a question regarding partial integrity. Obviously, the ability for the framework to support this concept of partial integrity is key. It's a key requirement from MIPI members because it can help reduce power consumption, heat dissipation, etc., etc. Can you talk about, again, this notion of partial integrity, why it's important, how it's been achieved through the implementation of these stride patterns? I think it's probably worth us spending just a few more minutes on this important subject. Again, perhaps Rick first.
Sure. So, well, first of all, it might be counterintuitive to a security expert or to a security practitioner in that you're only MAC protecting some of the data. Yeah, this is, this struck many of the work group members as somewhat odd at the beginning. So there's a couple ways to circumvent it from a security perspective, and that is, on a periodic basis, change the stride pattern, so that an attacker would never see the same attack surface, if you like. But in terms of the utility of it, this should be contrast against a link layer security protection level like MACsec that protects all the data all the time. With tens of sensors in the car, heat, power consumption is a reality. So partial integrity provides some relaxation or some ability to to process less, and then mitigate it, if you like, through changing the stride pattern. So a sensor's worst enemy in some sense is heat. This will help mitigate heat, thermals and things of that nature. But it needs to be used carefully, because there's the argument that it does kind of increase the threat, if you like, of attack.
Okay, thank you, Rick. I guess perhaps one last question. Why did MIPI base this framework around SPDM? Obviously, SPDM maybe is a standard that many perhaps may not be too familiar with. Maybe in the security world, we've probably heard of models such as TLS, but less so, or less of us will have heard about SPDM. So why did MIPI head down this route? Perhaps Phil, you'd be able to talk to this point.
Sure. DMTF, who developed SPDM, they saw the need for securing connections between compute components in place scenarios like cloud servers. Not just that. There's other connections as well. They saw that there were a need to have the ability to authenticate and establish secure connections and retrieve measurements. And yeah, so this, they're looking at components, they're looking at embedded design, and compute applications share similarities with automotive applications in that there will be central entities like the SoC in a automotive, which will initiate the security and be wanting to control a set of attached peripherals. And so this worked. This model suited MIPI quite well. Also, it's designed to be easy for wired connections, for wired connectivity, compared to TLS 1.3, which is designed more for the internet, for going over internet protocol messages. So that's why we ended up going with SPDM.
Okay, thank you, Phil. So we're a little bit over time, so I think it's probably apt that we wrap up. Phil, Rick, any last comments from either of you?
Well, I mean, maybe just a request to, you know, if there is interest, you know, get in touch with us with any follow-up. You know, the work group meets every week. There's typically a good crowd of regulars. You know, if there is sufficient interest to, you know, to contribute, you know, most welcome.
Yeah, very good point. So obviously, if we've got MIPI members on the line, they're more welcome to reach out to us through the group. If you're not a MIPI member, obviously, please come to us via this admin@mipi.org email address. That'll come through to myself and the marketing team, and we'll address how you can get involved with this activity. Obviously, you can find more information on our website, and there's some pre-existing sessions from our recent events that you can find links to on the screen here. Before we wrap up, I think the only last point to make is that we've got a MIPI DevCon coming up later this year in June. Call for papers is currently open, so if you're keen to come and present on a MIPI topic, please submit your proposition ASAP. I think that probably draws this particular session to a close. So Rick, Phil, thank you very much for presenting today, and obviously, as we mentioned a couple of times already, we'll get this recording available on demand ASAP in the next 48 hours or so. So thank you, gentlemen. Let's call it a wrap. Thank you.
Thanks for attending, everyone. Bye.